Now that you know a little bit about what a reentrant lock is conceptually and a mutex is conceptually, let's start to dig a little deeper into the structure and functionality of Java's ReentrantLock class. And you'll see that it's got a very interesting structure and a very interesting functionality. And this will look actually reminiscent to things we've talked about before when we talked about semaphore, because they follow basically the same design pattern. So a ReentrantLock is a class that can be used to provide mutual exclusion to concurrent Java programs. That's its role in life. It implements the lock interface. And I strongly recommend that you take a look at the documentation for the lock interface. It explains quite nicely the semantics of the different methods like lock and unlock and try lock and so on. It's very well written. Internally, the implementation of ReentrantLock applies the gang of four bridge pattern. So hopefully you learned something about the bridge pattern when you were taking the CS Intermediate Software Design course, CS 3251. And you may have wondered, does this stuff ever get used in practice? And the answer is absolutely yes. And this is a great example of how it gets used. The bridge pattern, for those of you who have forgotten, is basically a pattern that decouples an interface from its implementations, emphasis on plural. So in this case, fair and non-fair semantics of locking can be supported in a uniform way. And we'll see that this is just the classic bridge pattern in every way, shape, and form. You have the ReentrantLock, which is the abstraction part of that pattern. It contains a reference to an instance of either fair sync or non-fair sync, which themselves implement or extend rather the sync superclass, and we'll talk more about that in a second. And every time a method is called on ReentrantLock, it forwards to the appropriate method in either fair sync or non-fair sync, and the selection of these two things is done when the ReentrantLock is initialized, and you'll see how that works in a second. So great example of the bridge pattern. Go gang of four. Here's how we handle the hierarchy that is used to provide fair and non-fair semantics. There's this class called sync. We'll talk about that in a second. And the sync class has a field called sync, just differentiated by the capital letters. The capital one is the class, the lowercase one is the field. And you can see here that the sync class, which we use here, extends abstract queued synchronizer. And again, that should be very familiar to you because that's exactly the way things worked with Java semaphore. Same kind of idea. The Java semaphore also had a sync field, and the sync class extended abstract queued synchronizer, and so on and so forth. Abstract queued synchronizer is used by a number of Java synchronizers like ReentrantLock, Java condition object, Java Java semaphore, and so on, and other ones too, in order to be able to have FIFO wait queues. So it's basically a framework that can be reused for a bunch of different kinds of synchronization mechanisms. And if you want to learn more about the abstract queued synchronizer class, take a look at this paper written by my good friend and colleague Doug Lee. Now, in the ReentrantLock implementation, they take the sync abstract class. You can see it's an abstract class. That means some of the methods weren't filled in. And then they further extend to create a non-fair sync and fair sync pair of classes by extending sync. And that's where the bulk of the things that relate to fair versus non-fair ReentrantLock semantics reside. But of course, there's lots of sharing and reusability going on with both sync and abstract queued synchronizer. So non-fair sync and fair sync are subclasses that implement non-FIFO and FIFO semantics respectively. The way you select which semantic you would like is by passing in a Boolean to the ReentrantLock constructor. And as you can see here, the Boolean is called fair. And in this case, it uses the same pattern as we'll see in the semaphore and the ReentrantReadWriteLock class. If the semaphore is, if the Boolean is true, then it makes a fair sync. And if it's false, it makes a non-fair sync. What's the difference? Just as with semaphores, fair sync ensures FIFO fairness. So threads that are waiting to acquire the ReentrantLock will wait in the order. They'll be granted access to the lock in the order they're waiting, just like a typical queue that you would see at a movie or the airport or whatnot. For non-fair sync, however, there's no FIFO queuing. So it's possible for a thread that has just shown up to get access to the lock and ones that have been waiting for a longer time to be precluded at that moment from getting the lock. So basically the trade-off is between fairness versus performance. It's faster to implement a non-fair model. It's slower to implement a fair model, but it's fair. So you have to decide what you want. Now, a lot of times it doesn't matter, in which case you should go with the non-fair semantic. In fact, to underscore that, the ReentrantLock constructor that takes no parameters defaults to the non-fair sync semantic, which is exactly what you'd want it to do. Because if you don't care, it takes the fast route. You do care in some cases, and we will be caring in some cases, as you'll see when we go further along in the class and the assignments. Fair sync is generally much, much slower than non-fair sync, so use it accordingly, use it sparingly. When you need it, you need it. If you don't need it, don't do it. Now, ReentrantLock defines a protocol that's very similar to the monitor lock that's provided by Java's built-in monitor objects. And I haven't talked a whole lot about built-in monitor objects yet. We will cover that at some point because you'll get a chance to use it for some of your assignments. In fact, we'll probably cover it fairly soon. The key thing to remember about the built-in monitor objects is they're baked into the Java language itself, the Java execution environment, the Java virtual machine. They all have support for so-called built-in monitor objects. And you get those semantics by using the synchronized keyword, either a synchronized method or a synchronized block. ReentrantLock also has a similar protocol in that it has lock and unlock, which are kind of like the synchronized keyword, where you will have the system automatically acquire the intrinsic lock or the monitor lock when you go through the synchronized keyword and then release it on the way out using scoping. But as we'll see, the ReentrantLock goes above and beyond that. So lock acquires a lock and unlock attempts to release the lock. And I say attempts because if you call unlock and you don't own the lock, then bad things should happen. Just like your spin lock implementation, where it should throw the illegal state exception or whatever it was, illegal monitor state exception, I think it was, if you try to release a spin lock that you don't lock, you haven't locked. There's also a boatload of other things that ReentrantLock provides, which come from the lock interface, and this includes lock interruptibly, try lock, and there's actually two variants of try lock. One that will be using a timeout to wait for a certain amount of time to try to get the lock, and the other will just check right away and return immediately if it can't get the lock. Now, as you might infer from the name lock interruptibly, that means that lock by default is going to be uninterruptible. So by default, when you call lock, it will block until you get the lock. It will not be interrupted. But lock interruptibly allows the thread that's waiting for the acquisition of that lock to be interrupted through the interrupted method that we've talked about before. And we'll talk about that again more later. So you can see lock interruptibly gives you these extended capabilities to allow interruptibility, so you can have the disturb, please do disturb, that's what lock interruptibly does. And then try lock, these are non-blocking. Try lock with no parameters, we'll just check to see if the lock is available and then return false if it's not, otherwise it returns true if it gets it. And then you can also do it with a timeout. So this is a little bit subtle. Java's synchronized methods and synchronized statements are not interruptible. You cannot interrupt them, and that's actually a big design issue with Java built-in monitor object intrinsic locks, as they're called, which is probably why you want to avoid using them in most cases nowadays. Back in Java 1, that was the only game in town, but once Java 5 came along with all this good stuff, you want to stick with things like ReentrantLock whenever you can. Likewise, Java's synchronized methods and statements are also not non-blocking. So you can't do a try lock on the synchronized method or the synchronized statement. So they will always block. They are not non-blocking. So that's the end of the overview of the structure and functionality of Java ReentrantLock. As you can see, it's actually a fairly simple API, which it inherits from the lock interface, but it's very useful. And we'll talk further as we go into the next set of slides about some of the other interesting semantics of Java ReentrantLock, in particular, the reentrant part and what that means.